All right, so we're going to start talking about section 5.2, power functions and polynomial functions. I'll admit mostly polynomial functions is what we're going to look at. But first of all, just a definition, what is a power function? A power function is a function that can be expressed in this form where k and p are real numbers and k is known as the coefficient. So that would be a power function. Similar to a polynomial function, except notice that this is a single term. This is a monomial, the power function, whereas a polynomial function, it's kind of like made up of like the sum or difference of, several power functions. So you've got, as you go through here, you have things like, and I'll just give you an example. I know this looks rather intimidating, but you guys have seen lots of these, like 3x cubed plus 2x squared minus 5. I'll leave out the x term. That would be a polynomial function. So we've done a lot of those, and that's what we're primarily going to be working on in chapter, the first half of chapter 5. So this next part just asks you to identify, is it a power function, a polynomial function, or neither? And notice for this first one, this is neither. And the reason why is the variable cannot be in the exponent. And when that is the case, that's actually called an exponential function. That's what we're going to kind of look at in another unit, but right now this is not. So it's not a power, it's not a polynomial. On part B, it is a power function. Notice it is a single term. The coefficient is 1, and then the power is 6. It's also a polynomial function. It's a monomial because it only has one term. Terms are separated by plus and minus signs. Part C clearly is not because it's not a single term, so it's not a power function. However, it is a polynomial function. And if you were to write this out, and you don't have to, but if you were to multiply this x minus 4 quantity squared and then come up with that and then multiply that by x plus 2, you can put it in a box, a larger box, and then distribute the 2x, you could come up with an expression that would be a polynomial expression. And this last one, this is a power. So we have a power function. Now think of this, remember if it's in the denominator like this, we can think of this as x to the minus 2. So it's okay if the power is negative, it still can be considered a power function because notice what this says up here, p is a real number. However, this is not a polynomial. So notice the difference between part B, that's x to the 6, and I said that was a polynomial as well as power. For a power function, the power has to be a real number. Well, negative 2 is a real number. But for a polynomial function, the power, notice the degree in has to be a non-negative integer. So it has to be, negative 2 would be a negative integer, so that one won't work. So it's not a polynomial function, but it is a power. All right, so for different polynomials, if you just have f of x equals 2, remember this is like having y equals 2. So you're familiar maybe with that. I mean, we're getting more familiar with function notation. So this actually, the function name, we would just call this a constant. The degree for n is 0. I could write this as y equals 2 times n to the 0 power, because remember, anything to the 0 power is equal to 1, and then 2 times 1 would just be 2. So 0 is our degree. The leading coefficient is the coefficient that is in front of that degree, so we would have a 2. For f of x equals 5x minus 1, we recognize this as being linear. The degree would be 1. Remember, this is like a first power if there's not one there. And I guess, you know what, I should have said, because it's f of x, I should have had x to the 0 power. And the leading coefficient is 5. And for the next one, we recognize that as a quadratic So that is a quadratic function. The degree is 2 because it's the highest power. So yeah, there's a 1 there on the x term, but that's the linear term. But the highest power is a 2, so that's the degree of the polynomial. And the leading coefficient is the number that's being multiplied by that highest term. So we end up with a 4 for the leading coefficient. For the next one, it is a cubic function. The degree is 3. And for this one, the leading coefficient would be 2. And for the next one, it is a quartic. Now notice in here, because this you might think, well, wait a minute, are we allowed to have a square root? If the square root had extended and was over the x cubed, then that would be a problem. This would not be a polynomial, because then this power would be to the 3/2, and it would not be a non-negative integer because it wouldn't be an integer. So, but it's only over the square root of 2, so that's okay. So here we have the degree is 4. The leading coefficient, remember, if there's not one showing, it's like having a 1 there. So on this next part, nothing to write down, just to look at and talk about. Graphs of polynomials are smooth and continuous. There are no breaks, holes, or points. So we're looking for things that are smooth and continuous. We have a line. Here's our linear. This next one is, well, down here, going down is a quadratic function. Then we have a cubic function. We have a quartic function. We have something that's raised to the 5th power and to the 6th power. And you'll notice the difference between, actually they have some commonalities that we're going to talk about. And with the even powers, notice as the power increases, it kind of flattens out at the bottom. So what we're going to do now is use this idea of smooth and continuous and talk about which ones of these 3 graphs appear to be polynomial functions. Clearly right here, it's continuous, but it's not smooth. So this one would be no. It's not a polynomial. And I mean, it's smooth everywhere else. It's not smooth at x equals, I believe that's a 5, hard to read there. We recognize that hopefully as an absolute value function. This one is yes. It is smooth, curvy there, continuous. There's no holes or gaps that we can see. This one would be no. We have some points of discontinuity. It's not connected at x equals 1, so it is not continuous. It's not continuous at x equals 1 and at x equals 2. But notice it is continuous everywhere else. But when x equals 1, there's a jump right here. We actually call that a jump discontinuity. And at x equals 2, we have another jump discontinuity. For this next example, find the degree and the leading coefficient for the given polynomials. So the degree is just the highest power, but be careful. They kind of tried to trick you here. Normally, we put the highest power first. Here, they did not. So this is the term that would be the highest power. So we would have a degree of 5. Or we could say this is a 5th degree polynomial. And the leading coefficient is -6. Now, on this next one for g of x, you don't have to multiply this out. You could if you wanted to, but you don't have to. If I were to expand this part right here, all I really care about is this first term. And if I square the first term, square the 3 and the x, I'm going to get a 9x squared. And I'm going to have other stuff. I'm going to have, you could put the rest, there's other stuff there. But then I'm going to multiply the 9x squared by this x squared. So my leading term is going to be a 9x to the 4th. And then I'm going to have plus or minus some other stuff. But I don't care about that. To get the degree, so this is a 4th degree. And the leading coefficient is 9. Okay, now you could have multiplied it all out, but I didn't need to have the rest of it. I just needed that information. So on the next example, we are finding the x-intercepts. Finding the x-intercepts. So remember what the x-intercepts are. You let y equal 0, or in this case, you let g of x equal 0. And very kindly, this one is already factored for us. So because it's already factored, we could make use of the zero product property, which says that remember that we had A times B equals 0 means A equals 0 or B equals 0. So that was the zero product property. So we have x plus 5 equals 0, or x plus 2 equals 0, or x minus 4 equals 0. So we get x equals -5, -2, and 4, and those would be our x-intercepts. All right, now you got to be careful on this next one because there's, well, if you're actually just finding the intercepts, you could do x cubed minus 125 equals 0, x cubed equals 125, and if you cube root this, you get 5. However, if you factor x cubed minus 125, if you got out your factoring flowchart, this is the difference of two cubes. So when you have a cubed minus b cubed, it's a minus b times a squared minus ab plus b squared. That's the formula for the difference of two squares. So if we factor this, we get x minus 5, and then we'd have x squared minus 5x plus 25. I'm just using the formula. And if you solved both of these, over here we get the x minus 5 equals 0. So that's where the x equals 5 comes from. But if we set this equal to 0, you actually would have to use the quadratic formula. And when you do, I'm just going to jump right to it. You're going to end up with 5 plus or minus 5i root 3 over 2 if you use the quadratic formula. So these would not be intercepts because they are imaginary. But there would be a possibility that might not be the case. You might actually have to use the formula like this because if they could have been real solutions instead. It's possible to have 3 x-intercepts, and so you would need to be aware of that. So there's a possibility. So hopefully you keep that factoring flowchart handy if you need those formulas. On part C, you could do a modified diamond in a box to do this, to factor it. So that would make the sum a 24, the product a 24, the sum 11. So we have an 8 and a 3, but you need to use the box for that. So we have a 2x squared and a 12. I'll put the 8x here and the 3x here. Factor out a 2x, that makes this an x, a plus 4, and a plus 3. So I get 2x plus 3. And then this would be an x plus 4, and we want to set that equal to 0. So we get 2x plus 3 equals 0, or x plus 4 equals 0. So here we'll have x if we subtract 3 and divide by 2, and here we subtract 4. So those would be our two intercepts. Okay, so in behavior of graphs of polynomial functions, in behavior is just talking about what happens when x gets really large and x gets really small. So suppose that a times x to the n is the dominating term of a polynomial function. So that means that it's the term with the highest power, because it's going to be the one that has the biggest impact on on the value of the function. So suppose that it has an odd degree, which means the highest power is an odd degree. So for example, this could be something like f of x equals 3x cubed. Okay, suppose this is the highest power in my polynomial is x cubed. Well, that's an odd degree, so that's why we're talking about that. So if a is greater than 0, which in this case it is, then as x goes to infinity, or you can think of it as x gets larger, then f of x will also go to infinity. Think about the graph of this curve. If you were to graph this, it's going to be something like this, kind of have that shape to it. So as x gets larger, f of x gets larger. As x gets smaller in the negative direction, f of x also gets smaller in the negative direction. If a is negative, for example, if f of x is negative 3x cubed. Well, think about, we talked about in the last section, what happens if you have a negative in front of that? Well, that's going to reflect it. Remember with our functions, actually, this was in the last chapter, that's going to reflect it across the x-axis. So that means instead of this first picture I had, it's going to do something like this instead. So the part that went up now goes down, the part that went down now goes up. So as x gets larger, goes to infinity, f of x, notice, is getting smaller, goes to negative infinity. And as x goes to negative infinity, gets smaller, notice f of x goes to infinity, or it gets larger. Suppose that we have an even degree. So same situation, but now it's an even degree. So for example, let's suppose we had f of x equals 3x to the fourth. And if you were to look at that graph, it's going to look like a parabola. As a matter of fact, I think we have one of these right here. Here's x to the fourth. So it's going to look kind of like a parabola. 3x to the fourth is just going to be vertically stretched. So you have something like this. Now notice as x goes to positive and negative infinity, they go the same direction. So you can actually put this into one statement. You don't have to do two statements like up here. These went different directions. One end went up, one end went down. These are going the same direction. So if it's positive, if this value, the coefficient, is positive, then f of x goes to infinity, positive infinity. We don't need to put the positive. And for this last one, I'll do an example. Let's just make this negative 5x squared. So you're going to have something that looks like vertically stretched parabola, still the vertex at 0, 0. But notice now it's opening down. So as x goes to positive or negative infinity, whether x is getting larger or x is getting smaller, notice the y values, f of x, is going to negative infinity. Okay, so it's really the direction that is going. So that's how we describe the end behavior. When we talk in calculus, we'll use something with limits, but we'll go ahead and just leave it like this. When we're back in class, I might show you end behavior using limits. So for example, determine the end behavior of the functions, graph on your calculator to confirm. So to do this, we need to have a statement. Now, because this is the dominating term is even, I can do the statement where I combine it together. So I'm going to say, as x goes to positive or negative infinity, this is positive, so I'm going to have f of x goes to positive infinity, because both ends would be up. So here's a graph of that function, and I do want to point out to you, notice that in the middle, because we have an unusual shape, it kind of twists and turns a little bit. We're going to learn more about those things later, but this is end behavior. I'm just talking about what happens when x gets really large or x gets really small, and notice both ends are going up, so we would say f of x is tending towards infinity on both sides. Okay, so for the next one. Now, notice that if you want, you could multiply, you could distribute each of these, but you really don't have to. Really, all you need is the dominating term, which is this one right here, which is going to be 3x. Remember, when you're multiplying and the bases are the same, you add the exponents. So we get 3x to the fifth. That's the dominating term. So when we want to know the end behavior, so as x goes to infinity, because I need two statements now because this is an odd degree, we're going to have f of x goes to infinity. The right end is going to be up because this is positive. And as x goes to negative infinity, f of x also goes to negative infinity. As x gets larger, f of x gets larger. As x gets smaller, f of x gets smaller. That's really all that's saying. For the next one, here is the dominating term. This is even, which means I can do it in one statement. I guess I didn't graph this. You can graph this later to see what that looks like and confirm that the right end is up and the left end is down. On this one, now I know it's even, and there might be some twists and turns like this. It might do something like that, but both ends are going to be down because that's the end behavior. It's even, so I'm going to say as x goes to positive or negative infinity, I can do it in one statement because they go the same direction, f of x goes to negative infinity. So I graphed it. It's not exactly like my picture looked, as I can see here, but it does have a little bit of a twist. It comes up to a maximum, and then it kind of has a little twist here as well. But you can see the end behavior. Both ends are down. Okay, so for this next one, if you multiplied out, we have an x, and notice the minus sign in front of it, we have a negative x. So if I multiplied this out, I'm going to end up with a negative, and I know that there will be a coefficient as well. I'm not worried about that. I don't know, it doesn't matter what the numerical part is. I can see I'm going to have a negative x cubed. Okay, there's going to be a number here, but it's going to involve, actually it's not, but because it's just an x and an x and an x. So I'm going to have a negative x cubed. So that's enough to get the end behavior. I don't have to know the rest of the numbers in there. I don't have to multiply this all out. So it's an odd degree polynomial. So because of that, I know that they're going to go opposite directions, and this is negative. So as x approaches infinity, f of x is going to go to negative infinity. So this is going to be one like this second example that I did. So then as x goes to negative infinity, f of x goes to infinity. And then you can confirm that, and you can actually type into your graph parentheses x minus 5 times parentheses x plus 2 times parentheses 3 minus x. You don't have to multiply it out to graph it. And you can verify that you get end behavior that looks like that. So this next question says, what are turning points? Well, it's just like it sounds. It's where a function goes from one direction to another. And how can they help us determine the shape or degree of the polynomial? So first I'll answer that first question. It's where functions change from increasing to decreasing, or vice versa, because it can be the other way, go from decreasing to increasing. So that's how we can tell where there's a turning point. The maximum number of turning points is one less than the degree. Now, notice it says the maximum number of turning points. There could be less than that, but that's the maximum. So then in this example, it says determine the least possible degree of the polynomial function. Well, notice that it's increasing from negative infinity to maybe negative 10, and then it changes directions. So there's a turning point. So we have so right here is a turning point. Notice that my turning points are also where I'm going to find my relative maxes and mins. And here's a turning point. So since this has two turning points, then the least possible degree this could have is a third degree polynomial. Okay, that's the least degree. So it could be a 5th degree polynomial or a 7th degree polynomial, but the least degree it can be is 3 because there are 2 turning points, and the turning points is 1 less than the degree. This one, we have a turning point right here, 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 and here. So we have 4 turning points. And again, notice that those turning points occur where I have maxes or min. So I have a relative max, relative min, relative max, relative min. Notice there are no absolute maxes or mins because of my in behavior on this function. So this would be, the least would be, so the least degree is 5. So that means it can't be a 3rd degree polynomial because it has too many turning points. The least it could be is the 5th degree. It could be a 7th degree. But again, that's the least. So that takes us through this packet of notes. So that should get you through your assignment for today.